Okay. The topic I'm going to be covering today is related rates. I know it's kind of a confusing topic, which is why I'm here to explain it. And basically, related rates is when you find the rate of change at a specific point in time while the rate of change is changing. It might sound confusing, but I'll explain. Okay. So we'll start with an example problem. In this problem, you watch a balloon rising 500 feet away horizontally, and the angle from the ground between you and the balloon is increasing at a rate of 0.414 radians a second. How fast is the balloon rising when theta equals pi over 4? Okay, so when doing related rates, the first step is always to draw a picture to make things clearer. So here you are, and there's a balloon over here, and it's 500 feet away horizontally, and we don't know how high it is because it's constantly rising, and we know theta is equal to pi over 4 at the instant. And we also know that theta is increasing at a rate of 0.14 radians a second. Okay, so that's the known information. Now the next step is to identify the variables and the constants so you can make a related rates equation. So we know that we don't know y, and we don't know dy dt, which is what we're trying to find, so I'll put a box around that. And we know theta is equal to pi over 4 radians, and d theta dt is 0.14 radians. Okay, so, and that x equals 500 feet. Okay. So the next step is to find a relationship in this problem and write it as an equation. So we know that tan theta is equal to y over 500, the definition of tangent. We can rearrange this and then take the derivative using implicit differentiation, which would look like this. Because we want to find dy dt, we're going to isolate y and then take the derivative of the equation. So equals y. Okay, so now we differentiate implicitly, and we get so we get that equation. That's our related rates equation. You always need to find one of these in every related rates problem in order to solve. So we take our variables that we found up here, and we plug them in down here to find dy dt, which is what we're searching for. So we get dy dt is equal to 500 secant squared. Theta is equal to pi over 4, and d theta dt is equal to 0.14 radians a second. So when these are all numerical values, so you just plug this into your calculator and you'll get your final answer. Dy dt is equal to 148 feet a second. Okay. So that's the first example problem. I'm going to do one more just for reinforcement. Here is a problem. Water runs into a conical tank at the rate 9 feet cubed a minute. The tank stands point down and has a height of 10 feet and a radius of 5 feet. How fast is the water level rising when the water is 6 feet deep? Okay, so first step is draw a picture. We have a conical tank that's pointed down. we have water at 6 feet high, and the tank is 10 feet high. And so this is the height. Here's the height, and this is x over here, because x is constantly changing as the tank gets filled with water, and so is h. Okay, so now we identify the variables that we know. We know h is equal to 6 at the point where we want to find how fast the water level is rising. But what we want to find is the HVT. That's what we don't know and what we're trying to find. Okay, we know we can find x using sorry. Okay. We also need to plug in these variables into the equation. We know that this is the radius is 5 feet. Also, sorry, I didn't mention that before. So using that, we can use Pythagorean theorem and similar triangles to find these two. So we use similar triangles. So this is the cone, and we know this is 10. We know this is 5, and this is x and h, and we know h is equal to 6. We know from using this we can use the theorem of similar triangles by dividing each with its corresponding side. And then we get this equation, x is equal to h over 2. So we found the relationship between x and h for the entire time the water level is rising. The relationship will always remain like that, x equals h over 2. Good. So now we find the equation that relates everything, and then we take its derivative implicitly to find what we're looking for. So, okay, so we need to find the equation that relates everything, and we'll just use the equation for the volume of a cone here. Volume is equal to 1/3 pi x squared h. Okay, so now we know that x equals h over 2, so we plug that into this equation to get only h in the equation. Because we get volume is equal to 1/3 pi h over 2 squared h, which is 1/3 pi h squared over 4h, which is equal to pi over 12h cubed. Okay, so we have volume equal to pi over 12h cubed, and we take we implicitly differentiate this equation, as you have to do with all related rates problems, to find the relationship. So this is the derivative of this equation. This is just simplification. So basically this is equal to this, and then I differentiated that in here. So now we plug in the variables that we know. We know that the volume runs into the conical tank at a rate of 9 feet cubed a minute. So we know dV dt, 9 is equal to pi over 4. And we know h squared is equal to, or we know h is equal to 6 feet. It tells us that right here when the water is 6 feet deep. So we can plug that in right here for h. 6 squared is 36. And then dHdt is what we are solving for, the change in height over time. So these are all numerical values. You can just plug it into your calculator and you get this. Okay, that's a pi, by the way. Didn't come out well in smart work. Okay, so I hope this helped. I hope you now understand how to do a related rates problem.